Light has no mass. Zero. Not a tiny amount. Not an almost nothing amount. Absolutely zero rest mass. And yet, light can push a mirror. It can move an atom. It can hold a living cell in place. It can shape the surface of a star. It can, in theory, propel a spacecraft across the solar system without a single drop of fuel. This makes no sense. Everything you were ever taught about momentum says it requires mass times velocity, no mass, no momentum, no push, and yet photons push things every single second of every single day. So where does this impossible momentum come from? How does something with no mass carry the force to move matter? Tonight, we're gonna find out. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something simple. Something you already understand intuitively, even if you've never put it into words. Momentum. You know what momentum feels like. You felt it your entire life. When you throw a ball, you feel the push against your hand as the ball leaves your fingers. The harder you throw it, the more it stings when someone catches it. When you push a shopping cart through a store, you can feel how much harder it is to stop when the cart is full compared to when it's empty. A heavier cart moving at the same speed is harder to bring to a halt. A bowling ball rolling towards the pins carries more punch than a tennis ball at the same speed. A truck barreling down the highway is far more dangerous than a bicycle at the same velocity. All of this is momentum. It's one of the most fundamental ideas in physics. And for centuries, the formula for momentum seemed perfectly clear. Momentum equals mass times velocity. If you know how much something weighs and how fast it's going, you can calculate its momentum. A 2-kilogram ball moving at 10 meters per second has a momentum of 20 kilogram meters per second. Double the mass, double the momentum, double the speed, double the momentum. Simple, clean, elegant. This formula was formalized by Isaac Newton in the late 1600s, and it worked beautifully for everything people encountered in everyday life. Cannonballs, horse-drawn carriages, falling apples, planets in their orbits. Everywhere physicists looked, momentum equaled mass times velocity. It was one of those rare equations that seemed so obviously true that questioning it felt almost absurd. And for more than 2 centuries, nobody needed to question it. The formula predicted the motion of objects with extraordinary accuracy. Engineers used it to build bridges and machines. Astronomers used it to predict the paths of comets. Soldiers used it to calculate the trajectories of artillery shells. Mass times velocity. That was momentum. End of story. Except it wasn't. Because there was a problem hiding in plain sight. A problem that wouldn't become apparent until physicists started studying something very different from cannonballs and carriages. They started studying light. Let's talk about what light actually is. Light is electromagnetic radiation. It's a ripple in the electromagnetic field, a disturbance that propagates through space. When you flip a light switch in your room, what happens is that electrons in the filament or the semiconductor get excited, and as they release energy, they emit tiny packets of this electromagnetic radiation. Each individual packet is called a photon. A photon is the smallest possible unit of light. You cannot have half a photon. You cannot shave a little bit off a photon and have a smaller piece of light. A photon is the fundamental, indivisible quantum of electromagnetic energy. It's a particle in the sense that it comes in discrete packets, but it's also a wave in the sense that it has a frequency and a wavelength and can interfere with other light waves. This dual nature, particle and wave simultaneously, is one of the deepest features of quantum physics. But for now, the critical fact about a photon is this. A photon has zero rest mass, not a small mass, not a nearly zero mass, exactly zero. This has been tested with extraordinary precision. Experiments have placed upper limits on the photon's rest mass that are so small, they're essentially zero. If the photon had even the tiniest rest mass, the laws of electromagnetism would behave differently than what we observe. Maxwell's equations, which govern all of electricity and magnetism, only work correctly if the photon's rest mass is precisely zero. And Maxwell's equations work. They work so well that they're among the most precisely confirmed equations in all of science. Now, I use the phrase rest mass very deliberately. And it's worth pausing to understand what that phrase means, because it's the hinge on which this entire story turns. Rest mass is the mass an object has when it's standing still, when it's at rest relative to you. If you put a rock on a scale, the mass reading you get is its rest mass. If you put a baseball in your hand and weigh it before throwing it, the reading you get is its rest mass. For every ordinary object you've ever encountered, rest mass is simply mass. It's the quantity that tells you how heavy the object is and how much it resists being pushed. Rest mass is the mass that goes into Newton's formula for momentum. Mass times velocity. The mass in that formula is rest mass. But here's the crucial thing. The concept of rest mass only makes sense for something that can be at rest. A rock can be at rest. A baseball can be at rest. You can be at rest. These are all objects with mass, and you can always find a frame of reference in which they're standing still. A photon cannot be at rest. A photon is never standing still, not because it happens to always be moving, the way a restless person happens to always be pacing around a room. A photon is never at rest because it is physically impossible for a photon to be at rest. A photon always travels at exactly the speed of light. It cannot go slower. It cannot stop. From the moment it's created to the moment it's absorbed, it moves at 300,000 kilometers per second. There is no frame of reference in which a photon is standing still. The concept doesn't even apply. So when we say a photon has zero rest mass, we mean that the quantity which would describe its mass if it were at rest is zero. But a photon is never at rest. This isn't a technicality or a loophole. It's the key to everything. The photon exists in a regime where the everyday concept of mass simply doesn't operate the way we expect. Newton's formula, mass times velocity, was built for objects that can start from rest and be accelerated. The photon doesn't fit into that framework. It never starts from rest. It's born at full speed. It lives its entire existence at full speed. And it carries momentum the entire time, not because of mass, but because of something deeper. Energy. So the photon has no rest mass. And here is where the paradox begins. Because if momentum equals mass times velocity, and the photon's mass is zero, then the photon's momentum should be 0 times the speed of light, which is 0. No momentum. None. A photon, according to Newton's formula, should not be able to push anything. It should pass through the universe like a ghost, carrying energy in some abstract sense, but never able to deliver a physical kick to any object it encounters. But that is not what happens. In laboratories all around the world, physicists have demonstrated beyond any doubt that light pushes things. Shine a powerful laser at a tiny mirror suspended on a fine wire, and the mirror moves. Focus a laser beam tightly enough, and you can trap a microscopic bead or a living cell. Holding it in place and moving it around using nothing but light. Point enough sunlight at a thin reflective sail in space, and the sail accelerates. Slowly, gently but measurably and continuously. Light from the sun pushes on everything it touches. It pushes on the dust in a comet's tail, sweeping it away from the sun so that the tail always points away from the sun regardless of which direction the comet is moving. It pushes on the surfaces of stars themselves. And in the most massive stars, radiation pressure, the pressure exerted by light, is so intense that it nearly tears the star apart. Light pushes matter. This is not theoretical. It is observed, measured, and used in real technology every single day. Optical tweezers, which use focused laser beams to manipulate microscopic objects, earned Arthur Ashkin a share of the Nobel Prize in Physics in 2018. Solar sail prototypes have been tested in orbit. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated solar sail propulsion in interplanetary space. Light has momentum. Real, measurable, physical momentum. And it exerts that momentum on matter whenever it is absorbed, reflected, or scattered. So something is wrong. Not wrong with the experiments. The experiments are clear. Something is wrong with our formula. Momentum equals mass times. Velocity works perfectly for baseballs and bowling balls and trucks on the highway. But it fails for photons. It gives the wrong answer. It says photon momentum should be 0, but photon momentum is not 0. This means the formula is incomplete. This is an important distinction. The formula is not wrong for everyday objects. It's still perfectly accurate for anything moving at ordinary speeds with ordinary mass. But it's incomplete. It doesn't cover every case. It's a special case of something more general, like how a circle is a special case of an ellipse. The circle isn't wrong, it's just not the whole picture. The whole picture came from Albert Einstein. In 1905, Einstein published his theory of special relativity. Among its many revolutionary implications was a new, deeper understanding of the relationship between energy, momentum, and mass. Newton's physics treated mass, energy, and momentum as related but somewhat separate concepts. Einstein showed they were far more intimately connected than anyone had realized. The key equation is not the one most people know. Most people have heard of E equals mc squared. That equation is real and it's important. It tells you how much energy is locked inside a given amount of mass. But that equation is actually a simplified version. It applies only to an object that is standing still, an object at rest. It tells you the rest energy of a massive object. The full equation, the complete relationship between energy, momentum, and mass is more involved. In words, it says that the total energy of a particle squared is equal to its momentum, times the speed of light. That quantity squared, plus its rest mass times the speed of light squared, that quantity squared. Energy squared equals momentum squared, times the speed of light squared, plus rest mass squared times the speed of light to the 4th power. This is the equation that governs everything. Every particle, every object, every system in the universe. And the beautiful thing about this equation is what happens when you set the rest mass to 0. If the rest mass is 0, then the entire second term vanishes. The rest mass squared times the speed of light to the 4th power becomes 0. And you're left with total energy squared equals momentum squared times the speed of light squared. Take the square root of both sides and you get total energy equals momentum times the speed of light. Rearrange that, and momentum equals total energy divided by the speed of light. This is the equation for photon momentum. Momentum equals energy divided by the speed of light. There is no mass anywhere in this formula. Mass has dropped out completely. It's not needed. It was never the fundamental source of momentum. Mass was one way to have momentum, but was never the only way. Energy itself, moving through space at the speed of light, carries momentum. A photon with energy carries momentum in exact proportion to that energy. More energy means more momentum. Less energy means less momentum. Zero energy would mean zero momentum, but a photon with zero energy doesn't exist. It wouldn't be a photon. Every real photon has some energy, and therefore every real photon has some momentum. Now let's connect this to something more tangible, because a photon's energy is not some abstract number. It's directly tied to a physical property you can observe. Its frequency. In 1900, the German physicist Max Planck discovered something remarkable about energy and light. He found that electromagnetic radiation is not emitted or absorbed continuously in any amount you want. It comes in discrete packets, quanta, and the energy of each quantum is directly proportional to the frequency of the radiation. The relationship is beautifully simple. Energy equals h times F, where h is Planck's constant, a tiny but fundamental number woven into the fabric of quantum physics, and F is the frequency of the light. But Planck's discovery was mathematical. He proposed the quantum as a calculation trick, a way to make the equations work. He wasn't entirely sure the quanta were physically real. It took another discovery 5 years later to show that individual photons are not just mathematical conveniences. They are real, physical things that carry energy in specific, discrete amounts. In 1905, the same year he published Special Relativity, Einstein tackled a puzzle called the photoelectric effect. The phenomenon had been observed since the 1880s, when the German physicist Heinrich Hertz noticed that ultraviolet light striking a metal surface could cause the metal to emit electrons. Later experiments, particularly by the Hungarian-German physicist Philipp Lenard, revealed something deeply strange. When you shine light on a metal, the energy of the electrons that pop out depends on the frequency of the light, not on its brightness. Red light, no matter how intense, cannot eject electrons from certain metals. But even a faint beam of ultraviolet light ejects them immediately. Increasing the brightness of the ultraviolet increases the number of electrons. But each individual electron comes out with the same energy regardless of whether the beam is faint or blinding. This made no sense if light was a classical wave. A wave's energy depends on its amplitude, its brightness. A brighter wave should deliver more energy and knock electrons out harder. But that isn't what happens. Frequency determines the energy of each ejected electron, not brightness. Einstein explained this perfectly by proposing that light really does come in individual packets, photons, each carrying an energy determined by its frequency through Planck's relation, energy equals h times F. When a photon strikes an electron in the metal, it delivers all its energy in one shot. If that energy is enough to overcome the force holding the electron in the metal, the electron escapes. If the photon's energy is too low, if its frequency is too low, nothing happens. No amount of low-frequency photons will eject an electron, because each individual photon lacks the necessary energy. It's like trying to knock down a brick wall by throwing cotton balls at it. You can throw 1,000,000 cotton balls and the wall won't budge, but a single well-aimed hammer blow will chip it. The energy per impact matters, not the total number of impacts. This was the discovery that established the photon as a physically real particle, not just a mathematical convenience. It earned Einstein the Nobel Prize in Physics in 1921. Not for relativity, which is what most people associate with him, but for explaining the photoelectric effect. The Nobel Committee specifically cited his discovery of the law of the photoelectric effect, his demonstration that light comes in quanta with definite, individual energies. And here is why the photoelectric effect matters for our story. It established that a photon's energy is real and discrete. Each photon carries a specific amount of energy determined by its frequency. This is not an average over many photons. It's a property of every single photon individually. And once you know that each photon carries a definite energy, and once you know from Einstein's relativity that energy and momentum are fundamentally linked, then the conclusion is inescapable. Each photon must also carry a definite momentum. Frequency is how many times per second the electromagnetic wave oscillates. Red light oscillates at a lower frequency than blue light. Infrared oscillates at an even lower frequency. Ultraviolet oscillates at a higher frequency than visible light. X-rays oscillate at a much higher frequency still. Gamma rays oscillate at the highest frequencies of all. Because energy equals H times F, a gamma ray photon carries far more energy than a photon of visible light. An X-ray photon carries more energy than an ultraviolet photon. A blue photon carries more energy than a red photon. The higher the frequency, the more energy each individual photon carries. And now, remember, momentum equals energy divided by the speed of light. So if a gamma ray photon has more energy than a visible light photon, it also has more momentum. A blue photon carries slightly more momentum than a red photon. An X-ray photon carries significantly more momentum than either. A gamma ray photon packs the biggest punch of all. You can also express photon momentum in terms of wavelength instead of frequency. Since the speed of light equals frequency times wavelength, you can substitute and find that the momentum of a photon equals Planck's constant divided by the wavelength. This relationship was proposed by the French physicist Louis de Broglie in 1924 as part of his groundbreaking doctoral thesis. De Broglie suggested that just as light waves could behave like particles, particles of matter could behave like waves. The wavelength of any particle, he argued, is equal to Planck's constant divided by its momentum. For photons, this gives a clean, direct relationship. Shorter wavelength means more momentum, longer wavelength means less momentum. A gamma ray with an extremely short wavelength carries enormous momentum per photon. A radio wave with a wavelength stretching meters or even kilometers carries almost no momentum per photon. But here is something crucial that many people get wrong, and it's important enough that I want to say it clearly. Higher energy photons do not travel faster. A gamma ray photon and a radio wave photon both travel at exactly the same speed in vacuum. The speed of light. 300,000 kilometers per second. This is a fundamental constant of nature. It doesn't change based on the photon's energy, its frequency, or its wavelength. All photons in vacuum travel at exactly the same speed. What changes is the energy and momentum each photon carries, not how fast it moves. A gamma ray photon hits harder than a radio wave photon, not because it's faster, but because it carries more energy and therefore more momentum. Think of it this way. Imagine two identical trucks driving down the highway at exactly the same speed, say 100 kilometers per hour. One truck is empty. The other is fully loaded with cargo. They're both moving at the same speed, but the loaded truck has more momentum because it has more mass. Now, photons don't have mass, so this analogy isn't perfect, but the point is similar. Two photons moving at the same speed can carry different amounts of momentum because they carry different amounts of energy. Speed is not the only thing that determines how hard something hits. This resolves the paradox completely. Newton's formula, momentum equals mass times velocity, is not wrong. It's just a special case. It applies to objects with mass moving at speeds much slower than the speed of light. For those objects, it works beautifully, but it doesn't capture the full picture. The full picture provided by Einstein's relativity says that energy and momentum are fundamentally linked. Mass is one form of energy. So massive objects carry momentum through their mass and velocity, but energy can exist without rest mass. A photon carries energy purely through its frequency, through the oscillation of the electromagnetic field, and that energy automatically comes with momentum. You cannot have one without the other. This is not a loophole or a trick. It's not some peculiar exception that physicists had to bolt onto their theories. It's the natural, inevitable consequence of how energy, momentum, space, and time are related in our universe. Einstein's energy-momentum relation doesn't have a special exception clause for photons. The photon falls out naturally. Set the rest mass to 0 in the full equation, and you get photon momentum. It was always there, built into the deepest structure of physics. Let me put numbers on this so you can feel how real it is. A single photon of green light, the kind your eyes are most sensitive to, has a wavelength of about 550 nanometers. Its energy is about 3.6 times 10 to the minus 19 joules. That's an incredibly tiny amount of energy. And its momentum is about 1.2 times 10 to the minus 27 kilogram meters per second. That's an absurdly tiny amount of momentum. If a single green photon hit you in the hand, you would feel absolutely nothing. The push would be so small, it would be completely undetectable by any human sense. But photons don't arrive one at a time from ordinary sources. The sun emits roughly 10 to the 45th photons every single second. That is a 1 followed by 45 zeros every second. When sunlight falls on a surface, trillions upon trillions of photons strike it every moment, each one delivering its tiny kick. And those tiny kicks add up. They add up into a measurable force. A small force by everyday standards, but a real, physical, continuous force. This is why you never notice light pushing you when you step outside on a sunny day. The force of sunlight on your body is roughly a millionth of a Newton. That's far too small to feel. But on the scale of atoms, on the scale of thin reflective sails in the vacuum of space, on the scale of cosmic dust particles near a star, the force of light is not negligible at all. It's significant. It shapes the universe. And it all comes back to the simple, profound truth. Momentum does not require mass. Momentum requires energy moving through space. Mass times velocity is one way to have momentum, but it is not the definition of momentum. It is a special case. The complete definition connects momentum to energy, and energy can exist without rest mass. A photon carries energy. That energy has a frequency. That frequency determines the photon's momentum. And that momentum is real. It pushes real things. It moves real matter. But understanding that a photon must carry momentum because of the relationship between energy and momentum is only half the story. It tells you that photon momentum exists. It tells you how much momentum a photon has, but it doesn't tell you where that momentum comes from. After all, a photon doesn't pop into existence from nothing. Something creates it. Something emits it. An atom, a molecule, a hot filament, a nuclear reaction. Something has to give the photon its energy. And if the photon carries momentum, then the source must account for that momentum as well. Momentum doesn't just appear. It cannot be created from nothing. This is one of the most ironclad laws in all of physics. Conservation of momentum. The total momentum of any closed system never changes. So when a photon is born carrying momentum in one direction, something must recoil in the opposite direction to keep the books balanced. The question is not just whether photons have momentum. They do. The question is how the universe keeps its account straight when a new photon carrying real momentum suddenly exists where a moment ago it did not. That story, the story of emission and recoil and conservation, is where we're going next, because it reveals something even deeper about the nature of light. A photon does not start from rest and accelerate to the speed of light. It doesn't build up momentum gradually the way a car does when you press the gas pedal. A photon is born already moving at full speed, already carrying its full energy and its full momentum from the very first instant of its existence. And the system that created it pays the price in recoil. How that works and what it tells us about the fundamental nature of energy and motion is one of the most elegant stories in all of physics. There's a mistake people make when they try to picture how a photon gets its momentum. They imagine it the way they imagine a bullet leaving a gun. First, the bullet is sitting still inside the chamber. Then, the gunpowder ignites. The expanding gas accelerates the bullet from 0 to high speed in a fraction of a second. The bullet starts at rest, gains speed, and only once it reaches full velocity does it have its full momentum. People unconsciously assume the photon works the same way. It starts at rest inside the atom, then something happens. Some internal explosion or release, and the photon accelerates from 0 up to the speed of light, gradually picking up speed and momentum along the way. This picture is completely wrong. A photon never exists at rest. Not for a nanosecond. Not for a trillionth of a nanosecond. Not for any measurable or even theoretical interval of time. From the very first instant of its existence, a photon travels at the speed of light. It is born at full speed. There is no acceleration phase. There is no ramp up. The photon does not emerge slowly from the atom and then gather pace as it moves away. It is created already moving at 300,000 kilometers per second, already carrying its full energy, already oscillating at its full frequency, and already carrying its full momentum. The moment a photon exists, it is everything it will ever be. Its speed, its energy, its frequency, its wavelength, its momentum are all determined at the instant of creation. Nothing about the photon changes as it moves through empty space. It doesn't speed up. It doesn't slow down. It doesn't gain or lose momentum on its own. It simply travels, carrying everything it was born with, until it encounters something and is absorbed or scattered. This is radically different from how everyday objects behave. Every object you have ever interacted with started from rest and was pushed or pulled up to speed. Your car starts in the driveway and accelerates onto the highway. A ball starts in your hand and is thrown forward. Even a bullet starts at rest and is accelerated by expanding gas. But a photon skips the starting line entirely. It has no history of being at rest. It has no moment of zero velocity. The concepts of starting and accelerating simply do not apply. So if the photon doesn't acquire its momentum through acceleration, where does the momentum come from? The answer lies in the process that creates the photon, the act of emission. And understanding emission is the key to understanding everything about where photon momentum originates. Let's start with the simplest and most common case: an atom emitting a photon. Atoms are made of a nucleus surrounded by electrons. Those electrons exist in specific energy levels, like rungs on a ladder. An electron can sit on the third rung or the fifth rung, but it cannot sit between rungs. These energy levels are quantized, meaning they come in specific, discrete values with nothing in between. This was one of the great discoveries of early quantum physics, proposed by the Danish physicist Niels Bohr in 1913 and refined over the following decades into the full theory of quantum mechanics. When an electron sits in a higher energy level, the atom is in what physicists call an excited state. This state is usually unstable. The electron tends to drop down to a lower energy level, a more stable configuration, and when it does, the energy difference between the higher level and the lower level has to go somewhere. Energy cannot be destroyed, it must be conserved. So the atom releases that energy in the form of a photon. The energy of that photon is exactly equal to the energy difference between the two levels. If the electron drops from a level with 10 units of energy to a level with 6 units of energy, the photon carries away exactly 4 units of energy. Not roughly 4, not approximately 4, exactly 4. The books must balance perfectly. Now, here is where momentum enters the story. Before the electron drops, the atom might be sitting still. Its total momentum is 0. After the electron drops, a photon has been emitted. That photon carries momentum. We established in the previous discussion that any photon with energy automatically carries momentum equal to its energy divided by the speed of light. So now there is momentum in the system that wasn't there before. A photon is flying off in some direction carrying momentum, but momentum is conserved. The total momentum of the system, atom plus photon, must remain the same as it was before the emission. Before the emission, the total momentum was 0 because the atom was at rest. After the emission, the total momentum must still be 0. The photon carries momentum in one direction. So the atom must recoil in the opposite direction, carrying exactly the same amount of momentum, so that the two cancel out. This is exactly like a gun firing a bullet. Before the gun fires, the gun and bullet are both at rest. Total momentum is 0. After the gun fires, the bullet flies forward with momentum in one direction, and the gun kicks backward with equal momentum in the opposite direction. The total momentum remains 0. The atom does the same thing. It fires a photon in one direction and recoils in the opposite direction. The photon's forward momentum and the atom's backward momentum add up to 0. Exactly what they were before. Now, the atom's recoil is incredibly small. An atom is enormously more massive than a photon's equivalent energy would suggest. The recoil velocity of the atom is tiny. For a typical visible light photon emitted by a hydrogen atom, the atom recoils at a speed of only a few centimeters per second. You would never notice it. You could never feel it. But it is real. It is measurable. And it has been measured with extraordinary precision. One of the most elegant demonstrations of atomic recoil comes from a phenomenon discovered by the German physicist Rudolf Mossbauer in 1958. Mossbauer was studying gamma rays emitted by atomic nuclei, specifically by cobalt-57 nuclei decaying into iron-57. When a nucleus emits a gamma ray photon, it should recoil, just like any atom emitting any photon. That recoil changes the energy of the emitted gamma ray slightly, because some of the energy that would have gone into the photon instead goes into the kinetic energy of the recoiling nucleus. The gamma ray comes out with slightly less energy than the full energy difference between the nuclear states. What Mossbauer discovered was that when the emitting nucleus is locked tightly into a crystal lattice, the recoil is absorbed not by the single nucleus alone, but by the entire crystal. Because the crystal is so massive compared to a single nucleus, the recoil velocity becomes vanishingly small, and the energy lost to recoil becomes negligible. The gamma ray comes out with almost exactly the full transition energy. This effect, called the Mossbauer effect, allows physicists to produce gamma rays with incredibly precise, well-defined energies. It earned Rudolf Mossbauer the Nobel Prize in Physics in 1961, when he was just 32 years old. But here is why the Mossbauer effect matters for our story. It proves that recoil is real, and that it has measurable consequences. When the nucleus recoils freely, the gamma ray loses energy. When the recoil is suppressed by embedding the nucleus in a massive crystal, the gamma ray retains its full energy. The difference is detectable. The recoil is not a theoretical abstraction. It is a physical event that changes the energy and momentum of the emitted photon. Every photon emission event in the universe obeys this same principle. Every time a photon is created, the source recoils. An atom in a gas cloud in a distant nebula emits a photon and recoils in the opposite direction. A nucleus in a reactor emits a gamma ray and recoils. An electron in a light bulb filament drops to a lower energy level, emits a photon, and the atom containing that electron recoils. The sun emits roughly 10 to the 45 photons per second, and with every single one of those emissions, the particle or atom that emitted the photon recoils in the opposite direction. The recoil is real. The momentum accounting is exact. Not a single photon in the history of the universe has ever been created without a corresponding recoil somewhere in the system that produced it. Lasers offer another vivid example. A laser produces a concentrated beam of photons, all traveling in the same direction, all carrying momentum the same way. Because all the photons travel in the same direction, their momenta add up coherently. The laser itself must recoil in the opposite direction. This is measurable. If you mount a laser on a sensitive enough platform and turn it on, the platform moves. Very slightly, imperceptibly by human sensors, but it moves. The force is tiny for an ordinary laser pointer, but it is real. For high-powered industrial or military lasers producing thousands of watts of light, the recoil force becomes meaningful. It is small compared to mechanical forces, but it is not zero. Every photon leaving the laser carries momentum away from the device, and the device recoils. This principle is not limited to atoms and lasers. Any process that creates a photon involves an energy transition in some system, and that system recoils to conserve momentum. When an electron and a positron, its antimatter partner, annihilate each other, they produce photons. Typically 2 gamma-ray photons that fly off in opposite directions. Why opposite directions? because the electron and positron can be nearly at rest before annihilation, meaning the total momentum of the system is nearly zero. The two photons must carry equal and opposite momenta, so that the total momentum after annihilation is still zero. If only one photon were produced, it would carry momentum in one direction with nothing to balance it, violating conservation of momentum. Nature doesn't allow that. Two photons are produced, flying in opposite directions, each carrying momentum that precisely cancels the other. When a nuclear reaction in the core of a star produces a gamma-ray photon, the nucleus that emitted it recoils. That recoil nudges the nucleus slightly, changing its velocity. Over billions of emissions, these tiny recoils contribute to the motion and pressure inside the star. They are part of the mechanism that supports the star against gravitational collapse. The outward pressure of radiation inside a massive star is created by photons carrying momentum, pushing on matter as they work their way outward from the core. Every individual push is absurdly tiny, but there are so many photons, so many collisions, so many tiny kicks delivered every second that the cumulative effect is enormous. Enormous enough to help hold up a star that weighs 100 times more than the Sun. Now I want to address something deeper, because so far I've been talking about photon momentum as if it's a thing the photon carries, like a ball carrying kinetic energy. But that's not quite the right picture. A photon doesn't carry momentum the way a truck carries cargo. The momentum of a photon is not a substance stored inside it. It's a property of the electromagnetic field itself. This requires a small detour into what electromagnetic fields actually are and how they transport energy and momentum. And this part of the story begins with the Scottish physicist James Clerk Maxwell. In the 1860s, Maxwell unified electricity and magnetism into a single framework. He showed that electric fields and magnetic fields are not separate phenomena. They are two aspects of a single electromagnetic field. And he discovered that changes in this field propagate through space as waves, traveling at a specific speed. When he calculated that speed from the known properties of electricity and magnetism, the number came out to almost exactly the speed of light. Maxwell realized that light itself was an electromagnetic wave, but Maxwell's equations revealed something else, something that took decades for physicists to fully appreciate. The electromagnetic field doesn't just carry energy, it carries momentum. When an electromagnetic wave propagates through space, it transports both energy and momentum in the direction it's moving. This is not an addition or an approximation. It falls directly out of Maxwell's equations. The English physicist John Henry Poynting formalized this in 1884 with what is now called the Poynting vector, a mathematical quantity that describes the flow of energy carried by electromagnetic fields. And alongside the energy flow, there is always a corresponding momentum flow. This means that when we say a photon carries momentum, what we really mean is that the electromagnetic field, oscillating at a particular frequency and propagating in a particular direction, carries momentum. The photon is the quantum of this field. It's the smallest possible packet of electromagnetic energy and momentum. The momentum isn't something extra that gets attached to the photon. It's an intrinsic, inseparable property of the electromagnetic disturbance itself. You cannot have an electromagnetic wave with energy but no momentum. The two are bound together by Maxwell's equations and by Einstein's relativity. To build some physical intuition for this, think about what happens near a hot furnace. If you stand near an open furnace, you feel heat radiating outward. That heat is infrared radiation, which is electromagnetic waves, which means photons. Those photons carry energy, which is why you feel warm. But they also carry momentum. They are pushing you. Very gently, far too gently to feel, but they are pushing. The furnace radiates in all directions, and in every direction, the outgoing photons carry momentum away from the furnace. If you could somehow place a perfectly reflective shell around the furnace, the photons bouncing off the inside of that shell would exert a continuous outward pressure on it. This is radiation pressure from thermal emission. It's the same physics that operates inside a star, where the radiation from the core pushes outward against the weight of the star's own material. The electromagnetic field itself, vibrating and propagating outward, carries the momentum, not as cargo, but as an inherent property of the wave. Think of it like a wave on a taut rope. If you whip one end of a rope, a pulse travels along it. When that pulse reaches the other end, where the rope is tied to a post, it delivers a tug. The rope itself didn't carry a package to the post. The wave carried energy and momentum through the rope, and when it reached the end, it delivered a force. Electromagnetic waves do the same thing, except they don't need a rope. They propagate through empty space, through the electromagnetic field itself, and when they reach matter, they deliver their energy and momentum to it. This is why it's misleading to think of photon momentum as a substance stored inside the photon, like water in a bottle. The momentum is the field. The field carries energy, and that energy moving through space at the speed of light is momentum. There is no separation between the photon's energy and its momentum. They are the same physical phenomenon described in two different ways. Energy tells you how much. Momentum tells you how much and in which direction. A photon moving to the right with a certain energy has momentum to the right. The same photon moving to the left would have the same energy but momentum to the left. Energy is a scalar, a number without direction. Momentum is a vector, a number with direction. But they are locked together. For a photon, if you know one and you know the direction, you know the other. This also explains why the momentum doesn't run out. A photon crossing billions of light years of empty space doesn't gradually lose momentum along the way. It doesn't leak out. It doesn't fade. The electromagnetic disturbance propagates through vacuum without any resistance. There is nothing to slow it down, nothing to drain its momentum. A photon emitted by a star 12 billion years ago carries from its own perspective the same energy and momentum it was born with. The only thing that can change a photon's momentum is an interaction with matter or a gravitational field, which we will explore later. In empty space, the photon is eternal and unchanging. Let me bring all of this together with a clear step-by-step picture of what happens when a photon is created. Step 1. A system, let's say an atom, exists in an excited state. It has more energy than its ground state. Its total momentum might be 0 if it's at rest, or it might have some momentum if it's already moving. But whatever the total momentum is, that number is fixed before anything happens. Step 2. The atom undergoes a transition. An electron drops from a higher energy level to a lower one. The energy difference between those two levels determines the energy of the photon that will be emitted. The photon's frequency and wavelength are fixed by this energy through Planck's relation. Energy equals h times f. Step 3. At the instant the transition occurs, a photon is created. It does not accelerate. It does not ramp up. It appears already moving at the speed of light, already carrying its full energy, already oscillating at its determined frequency, and already carrying momentum equal to its energy divided by the speed of light. The photon's momentum is in the direction the photon is traveling. Step 4. The atom recoils. It picks up momentum in the opposite direction, equal in magnitude to the photon's momentum. The atom's recoil velocity is tiny, because the atom is so much more massive than the energy equivalent of the photon, but the recoil is real and exact. Step 5. After the emission, the total momentum of the system, atom plus photon, is exactly the same as it was before the emission. If the atom was at rest before, the total momentum was 0. After emission, the photon's forward momentum and the atom's backward momentum sum to 0. Momentum is conserved perfectly. Step 6. The photon propagates through space as an electromagnetic disturbance, carrying its energy and momentum with it. Nothing changes about the photon as it travels through vacuum. It moves at the speed of light, carrying its momentum intact, until it encounters matter. This is the complete origin story of photon momentum. The momentum doesn't come from nowhere. It doesn't materialize out of the vacuum. It doesn't require hidden mass. The photon's momentum is supplied by the energy transition in the emitting system, and the emitting system pays for it by recoiling. The universe's momentum books are balanced at every step. No exceptions, no loopholes, no violations. And this process is not limited to atoms. It happens in every system that emits electromagnetic radiation. When an accelerating electron radiates radio waves, the electron recoils. When a vibrating molecule emits infrared radiation, the molecule recoils. When a nuclear reaction produces gamma rays, the nucleus recoils. When matter and antimatter annihilate to produce photons, the photons carry away all the momentum, and the total remains conserved. Every emission event in the universe obeys the same rules. There's a profound philosophical point buried in all of this. Photon momentum is not something separate from the photon's creation. It's not an add-on feature, an afterthought, or a secondary property. The momentum is part of the photon's birth. The photon and its momentum come into existence together as a single, inseparable event. You cannot create a photon without creating its momentum. You cannot create a photon that moves in a direction without giving it momentum in that direction. The energy, the frequency, the direction, and the momentum are all one package, all determined simultaneously by the physics of the emission process. This is why asking where the photon's momentum comes from is actually the same as asking where the photon itself comes from. The answer is the same for both questions. The photon comes from an energy transition in a physical system. The momentum comes from that same energy transition. And the system that gave up the energy to create the photon also gave up the momentum, absorbing the recoil so that the total momentum of everything remains unchanged. Now the photon is out in the universe. It's traveling through space at the speed of light, carrying energy and momentum in a specific direction. The emitting atom is recoiling gently in the opposite direction. The universe's books are balanced. But the story isn't over, because eventually that photon is going to encounter something. Another atom, a mirror, a dust grain, a sail, a wall, the surface of a planet. And when it does, something has to happen to all that energy and all that momentum the photon is carrying. The photon must deliver its energy and momentum to whatever it hits. This is where photon momentum stops being an abstract concept and becomes a physical force, a force that pushes mirrors, traps cells, shapes stars, and could one day propel spacecraft between worlds. How that delivery works, and why reflection delivers a bigger kick than absorption, is the next piece of the puzzle. So now we have a photon flying through space. It was created in an emission event, born already at full speed, carrying energy and momentum from the very first instant of its existence. The source that created it recoiled to balance the books. Momentum was conserved perfectly. Everything is accounted for. But the photon's journey doesn't last forever. Eventually it's going to hit something. And when it does, all that energy and all that momentum have to go somewhere. The photon doesn't just vanish silently, it delivers its payload. And how it delivers that payload depends on what happens when it meets matter. There are three basic things that can happen to a photon when it encounters a material object. It can be absorbed, it can be reflected, or it can be scattered, which means it bounces off at a new angle, often with a different energy than it had before. Each of these interactions transfers momentum differently, and understanding the differences is the key to understanding how light pushes matter. Let's start with the simplest case, absorption. When a photon is absorbed by an object, the photon ceases to exist. Its energy is transferred entirely to the absorbing material. It might heat the material up. It might excite an electron to a higher energy level. It might break a chemical bond. But whatever form the energy takes, the photon itself is gone. It has been completely consumed. And here's the critical point. When the photon is absorbed, its momentum is also transferred to the absorbing object. The photon was carrying momentum in a specific direction. Now that momentum belongs to the object that absorbed it, the object receives a tiny push in the direction the photon was traveling. Think of it like catching a ball. When you catch a baseball, the ball stops moving, but its momentum doesn't vanish. It transfers to you. You feel the impact. Your hand stings. Your body moves backward slightly. The ball's momentum has become your momentum. The same thing happens when an object absorbs a photon. The photon stops existing, but its momentum transfers to the absorber. The absorber gets pushed in the direction the photon was traveling. How much momentum does the absorber receive? Exactly the amount the photon was carrying. For a single photon, this is incredibly small. A visible light photon carries momentum on the order of 10 to the minus 27 kilogram meters per second. This is so small that absorbing a single photon produces no detectable motion in any everyday object. We need a balance more sensitive than anything ever built to detect the recoil from a single visible light photon, absorbed by, say, a grain of sand. But photons don't arrive alone. They arrive in enormous numbers. Sunlight striking a surface delivers roughly 10 to the 21 photons per second per square meter. Each one delivers its tiny kick, and all those kicks point in the same general direction, the direction the light was traveling. The cumulative effect is a small but real force pushing the surface in the direction of the incoming light. Now let's consider reflection. And this is where things get more interesting, because reflection transfers more momentum than absorption does. When a photon reflects off a surface, it doesn't stop. It bounces back. It reverses direction. Before reflection, the photon was moving toward the surface, carrying momentum in that direction. After reflection, the photon is moving away from the surface in the opposite direction, carrying momentum the other way. Let's think carefully about what this means for the surface. Before the reflection, the photon carried momentum toward the surface, Call that positive momentum. After the reflection, the photon carries the same magnitude of momentum, but now in the opposite direction. Call that negative momentum. The change in the photon's momentum is the final momentum minus the initial momentum. That's negative momentum minus positive momentum. The photon's momentum changed by twice its original value. By conservation of momentum, whatever the photon lost, the surface gained. So the surface receives a momentum kick equal to twice the photon's original momentum. Twice. Not once, but twice. Reflection delivers double the push compared to absorption. This is a simple but powerful result. If you want light to push something as hard as possible, you don't want the surface to absorb the light. You want it to reflect the light. A perfectly reflective surface gets twice the momentum transfer of a perfectly absorbing surface. The photon hits, reverses direction, and in doing so, delivers double the kick. Let me make this concrete with an analogy. Imagine you're standing on an ice rink, nearly frictionless. Someone throws a ball at you. If you catch the ball, you absorb its momentum and slide backward. But if instead of catching it, you bat it back toward the thrower, you slide backward even more. You got the momentum from stopping the ball, plus additional momentum from pushing it back the other way. Reflection is like batting the ball back. Absorption is like catching it. Batting it back always pushes you harder. Now let's talk about the third interaction, scattering. Because scattering is different from both absorption and reflection, and it reveals something important about how flexible momentum transfer can be. When a photon scatters off an object, the photon doesn't disappear like in absorption, and it doesn't simply reverse direction like in ideal reflection. Instead, the photon bounces off at some angle, changing its direction of travel. And in many types of scattering, the photon also changes its energy. It might come out with less energy than it went in with, meaning it's been redshifted. Or in some cases, it might come out with more energy if the object it scattered off was already moving fast. The momentum transfer in scattering depends on the angle. If the photon barely deflects, just grazes the particle and continues nearly straight ahead, the momentum transfer to the particle is very small. The photon kept most of its original momentum direction, the particle received only a tiny sideways kick. But if the photon deflects through a large angle, say 90 degrees, the momentum transfer is much larger. And if the photon scatters straight backward, reversing its direction entirely, the momentum transfer is at its maximum, just like in reflection, 2 times the photon's original momentum. In general, scattering transfers somewhere between 0 and twice the photon's original momentum, depending on the angle. The exact amount depends on the geometry of the collision, the energy of the photon, and the mass and motion of the particle it hits. Scattering is incredibly common throughout the universe. When sunlight enters Earth's atmosphere, it scatters off nitrogen and oxygen molecules. This is why the sky is blue. Blue photons scatter more strongly than red photons because of their shorter wavelengths. Each time a blue photon scatters off an air molecule, it transfers a tiny amount of momentum to that molecule and changes direction. Multiply this by the countless trillions of scattering events happening in the atmosphere every second, and you get a measurable effect. The atmosphere itself is pushed outward very slightly by sunlight scattering within it. In interstellar space, photons from stars scatter off dust grains. Each scattering event pushes the dust grain a little. Over thousands of years, these tiny pushes can move dust grains across interstellar distances, slowly reshaping nebulae and dust clouds. Scattering is one of the mechanisms by which radiation pressure, the pressure of light, acts on diffuse material. The photons don't need to be absorbed to push matter. They can simply bounce off at an angle, transferring some of their momentum, and continue on their way. We will encounter the most dramatic example of scattering later, when we discuss a specific experiment involving X-ray photons bouncing off electrons. That experiment provided the most direct evidence ever recorded that photons carry definite momentum. But for now, the important point is that scattering is a third way photons transfer momentum to matter, alongside absorption and reflection. All three mechanisms are real. All three are happening constantly, and all three are expressions of the same underlying physics. Photons carry momentum, and when they interact with matter, they deliver some or all of that momentum to the material they encounter. Now, let's talk about radiation pressure, because this is the bridge between individual photon kicks and real forces that shape the universe. Radiation pressure is the pressure exerted by electromagnetic radiation on any surface that absorbs, reflects, or scatters it. It's caused by the cumulative momentum transfer of enormous numbers of photons striking the surface. Each individual photon delivers a momentum kick so tiny it's undetectable, but enough photons arriving fast enough create a continuous, measurable pressure. The concept of radiation pressure was predicted theoretically by James Clerk Maxwell in the 1870s, based on his electromagnetic theory. Maxwell showed mathematically that electromagnetic waves should exert pressure on any surface they strike, but the pressure is extraordinarily small by everyday standards. Sunlight at Earth's distance from the Sun exerts a radiation pressure of only about 4.7 millionths of a pascal on a perfectly absorbing surface. For comparison, atmospheric pressure at sea level is about 101,325 pascals. Radiation pressure from sunlight is roughly 20 billion times weaker than the air pressure pushing on you right now. For decades after Maxwell's prediction, radiation pressure remained purely theoretical. Physicists knew it should exist, but the force was so small that measuring it seemed nearly impossible. The challenge was to isolate the tiny push of light from all the other forces that could mimic it, particularly the heating effects that made nearby air molecules bounce off the detector. Any apparatus designed to measure radiation pressure had to eliminate those thermal effects, and in the late 19th century, that was extraordinarily difficult. The breakthrough came around 1900 and 1901, when two independent experiments succeeded in measuring radiation pressure directly for the first time. The Russian physicist Pyotr Lebedev published his results in 1900. He used a delicate torsion balance, a thin vein suspended on a fine fiber inside a partially evacuated glass vessel. When he shone light on the vein, it twisted, but Lebedev had to be incredibly careful. If the vacuum wasn't good enough, residual air molecules heated by the light would bounce off the vein and create a force that had nothing to do with radiation pressure. This thermal effect, called radiometric force, is actually much larger than radiation pressure at atmospheric pressure. It's what makes a Crooker's radiometer spin, the little device with black and white veins that you sometimes see in science museums. Those veins spin because of heated air molecules pushing on them, not because of photon momentum. To isolate true radiation pressure, Lebedev needed a very high vacuum and extremely precise measurements. Almost simultaneously, the American physicists Ernest Nichols and Gordon Hall performed a similar experiment at Dartmouth College in 1901. Their apparatus was also a torsion balance, but with a different design. They used small, silvered glass mirrors and carefully measured the twisting of a quartz fiber when light struck the mirrors. They compared the force on the reflecting side to the force on the absorbing side, and found that the reflective surface experienced greater force, consistent with the prediction that reflection transfers twice the momentum of absorption. Both experiments confirmed Maxwell's prediction. Light pushes matter. The measured pressure agreed with the theoretical value. These were landmark results, among the first direct demonstrations that electromagnetic waves carry momentum and deliver it to surfaces they strike. The forces were incredibly small, measured in billionths of a newton, but they were real and they matched theory precisely. This is why you don't feel sunlight pushing you. The force is real, but is overwhelmed by every other force acting on your body. Gravity, air pressure, friction, the tension in your muscles, all of these are billions of times stronger than the radiation pressure of sunlight. But here's the key insight. Radiation pressure becomes significant when three conditions are met. First, the light source must be intense, delivering enormous numbers of photons. Second, the surface must be large, collecting momentum from as many photons as possible. And third, other forces must be small, so that radiation pressure isn't drowned out by stronger effects. When these conditions are met, light becomes a real, practical force. Solar sails satisfy all three conditions. Sunlight is intense, delivering about 1,360 watts per square meter at Earth's distance from the sun. That's a lot of photons. Solar sails are designed to be large, sometimes tens of meters or even hundreds of meters across, to collect as many photons as possible. And in the vacuum of space, there is no air resistance, no friction, no drag. The only forces acting on a solar sail are gravity and radiation pressure. This is why solar sails are designed to be reflective, not absorptive. A solar sail covered in matte black material that absorbs all incoming sunlight would still experience a push, but it would be half the push of a perfectly reflective silver sail that bounces the light back. Engineers designing solar sails want maximum momentum transfer per photon, so they make the sails as reflective as possible. Nichols and Hull demonstrated this difference in their laboratory over a century ago. Solar sail engineers exploit exactly the same physics at interplanetary scale. The Japanese Space Agency launched a spacecraft called Icaros in 2010. Icaros carried a solar sail 14 meters across, a thin sheet of reflective material that unfurled in space. Sunlight striking the sail pushed it. The force was tiny, about 1.12 millinewtons. That's roughly the weight of a small ant on Earth. But in the vacuum of space, with no friction to oppose it, even that tiny force could produce continuous acceleration. Icaros became the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space. It proved that you can travel through the solar system using nothing but light. In 2019, the Planetary Society launched LightSail 2 into Earth orbit. This small spacecraft deployed a solar sail about 32 square meters in area, roughly the size of a boxing ring. Over the following months, sunlight pushed the sail, raising the spacecraft's orbit measurably. LightSail 2 demonstrated that solar sailing works not just in theory, not just in deep space, but in the practical environment of Earth orbit. The beauty of solar sailing is that the fuel is free and unlimited. A rocket carries its fuel with it. When the fuel runs out, the rocket stops accelerating. A solar sail uses sunlight as its fuel. As long as the sun is shining, the sail keeps accelerating. The acceleration is small, but it never stops. Over months and years, a solar sail can build up substantial velocity. Given enough time, a solar sail could reach speeds far greater than any chemical rocket. This is all possible because photons carry momentum. Each photon of sunlight hitting the reflective sail transfers twice its momentum to the sail. Each individual transfer is absurdly tiny. But 10 to the 21 photons per second per square meter, striking a sail tens of meters across, creates a force that can propel a spacecraft between planets. Momentum from massless particles pushing real hardware through real space. Now, let's shrink the scale dramatically, from spacecraft and planets down to individual living cells. Because photon momentum isn't just useful for pushing things through space, it's useful for pushing incredibly tiny things right here in a laboratory. Optical tweezers are devices that use tightly focused laser beams to trap and manipulate microscopic objects. A single cell, a bacterium, a tiny bead of glass, these can all be held in place, moved, rotated, and studied using nothing but focused light. The technique was pioneered by American physicist Arthur Ashkin, who spent decades developing it at Bell Laboratories. His work earned him a share of the Nobel Prize in Physics in 2018. The basic principle relies on two competing forces, both generated by photon momentum. The first force is called the scattering force. When a laser beam hits a small particle, some photons scatter off the surface. These scattered photons transfer momentum to the particle in the direction the beam is traveling, pushing the particle downstream along the beam. This is ordinary radiation pressure, the same force that pushes a solar sail. By itself, the scattering force would just push the particle away. You couldn't trap anything with it. But there's a second force, and this is the clever part. It's called the gradient force. When a laser beam is focused through a high-quality microscope objective, the intensity of the light isn't uniform. It's brightest at the focal point and dimmer everywhere else. A small transparent object, like a glass bead or a cell, bends the light passing through it. The bending changes the direction of the photons, and changing a photon's direction means changing its momentum. Near the edge of the beam, where the intensity drops off, more photons are passing through the side of the bead that faces the bright center than through the side that faces the dim edge. The bead refracts these photons, bending them outward. By Newton's third law, the momentum change of the photons produces a reaction force on the bead that points inward, toward the center of the beam, toward the region of highest intensity. This gradient force pulls the particle toward the focal point. If the gradient force is stronger than the scattering force that pushes the particle along, the particle gets trapped. It sits at the focal point, held in a three-dimensional cage of light. Push the focal point to the left, and the bead follows. Push it up, and the bead rises. You can move the trapped object in any direction simply by steering the laser beam. Think about what's happening here at the most fundamental level. Individual photons pass through the bead. The bead refracts them, bending their paths. Each photon that changes direction transfers momentum to the bead. The cumulative effect of billions of photons per second, all having their paths bent by the bead, creates a net force that holds the bead at the focus of the laser. If you move the laser, the bead moves with it. You're picking things up and carrying them with light. Optical tweezers have transformed biology and biophysics. Researchers use them to manipulate individual DNA molecules, measuring the forces required to stretch and unwind the double helix. They use them to study molecular motors, the tiny protein machines that move cargo along tracks inside living cells. They use them to measure the forces generated by single motor protein molecules, called kinesins, as they walk step by step along a microtubule track. They use them to study how white blood cells engulf bacteria by holding a bacterium in the laser trap and bringing it close to the cell surface. They use them to sort cells, position them on surfaces, and study how individual bacteria swim through fluids by tracking the forces the bacterium exerts against the optical trap as it tries to escape. Researchers have even used optical tweezers to measure the tiny forces generated by a single ribosome as it translates genetic code into protein, one amino acid at a time. All of this is done by exploiting the momentum of photons. Each photon that refracts through a trapped bead delivers a tiny kick, enough kicks per second, focused precisely enough, and you can hold a living cell in the palm of a laser beam. Now let's go to the opposite extreme of scale, from microscopic beads to the largest structures in the universe: stars. Radiation pressure doesn't just work in laboratories and on spacecraft. It operates inside every star that shines. And in the most massive, most luminous stars in the universe, radiation pressure is so powerful that it fundamentally determines the star's structure, its lifetime, and its ultimate fate. Inside a star, nuclear fusion in the core produces enormous quantities of energy. That energy works its way outward through the star as photons. These photons are constantly being absorbed and re-emitted by the dense stellar material. Each absorption transfers momentum from the photon to the material. Each re-emission sends a new photon outward, delivering another kick. The net effect is an outward push, a radiation pressure that acts against the inward pull of gravity. In a stable star, the inward pull of gravity is balanced by outward pressure. In smaller stars like the Sun, most of that outward push comes from the gas pressure, the sheer thermal energy of the hot plasma. But in the most massive and luminous stars, radiation pressure becomes the dominant force. It is the pressure of light, not gas, that holds these giants together. This balance is called hydrostatic equilibrium, and it is what keeps a star the size it is. The star doesn't collapse because radiation pressure supports it. The star doesn't explode because gravity holds it together. The two forces battle to a standstill, and the star shines steadily for millions of years. But there's a limit to how far this balance can go. If a star is too luminous, if it produces too many photons per second, the outward radiation pressure overwhelms gravity. Material from the star's outer layers gets blown away into space. The star cannot hold itself together. This limiting luminosity is called the Eddington luminosity, named after the British astrophysicist Arthur Eddington, who worked out the physics in the 1920s. The Eddington limit sets a practical ceiling on how massive a star can be. Stars more massive than about 150 times the mass of the Sun produce so much radiation that the outward pressure of their own light tears away their outer layers faster than gravity can hold them down. This is why you don't find stars with masses of 1,000 solar masses or 10,000 solar masses. The radiation they would produce would blow them apart almost immediately after they formed. Stars near the Eddington limit live violent lives. They shed tremendous amounts of mass through radiation-driven stellar winds. The star I2 Carinae, one of the most luminous stars known, has a mass of roughly 100 solar masses and a luminosity about 5 million times that of the Sun. Its radiation pressure is so intense that it drives a stellar wind carrying mass away at rates billions of times greater than the solar wind. I2 Carinae has erupted multiple times in recorded history. In the 1840s, It produced a massive eruption that briefly made it one of the brightest stars in the sky. During that eruption, it ejected roughly 10 to 20 solar masses of material into space, forming the spectacular homunculus nebula that surrounds it today. All of that mass was pushed away by photon momentum. Individual photons, each carrying a minuscule amount of momentum, but arriving in such incomprehensible numbers that their collective force overwhelmed the gravity of a star 100 times more massive than the Sun. Radiation pressure also shapes the environments around stars. Stellar winds driven by radiation pressure create bubbles in the interstellar medium, pushing gas and dust away from the star. When a massive star explodes as a supernova, the flash of radiation that precedes the shockwave carries enormous momentum. The radiation from the explosion can actually push material outward before the physical debris arrives. In the expanding remnants of supernovae, like the Crab Nebula, the central neutron star continues to emit intense radiation that energizes and shapes the surrounding nebula. In the accretion disks around black holes, radiation pressure plays a crucial role. As matter spirals inward toward a black hole, it heats up enormously, emitting intense radiation. If the rate of infall is high enough, the radiation pressure from the heated material can actually push infalling gas back outward, regulating how fast the black hole can consume matter. This is essentially the Eddington limit applied to accretion. The black hole can only eat so fast before its meal starts fighting back with photon momentum. Even at the scale of planetary systems being born, radiation pressure matters. When a young star ignites, the radiation pressure from its light begins pushing away the remaining gas and dust from the protoplanetary disk. This helps determine how long the disk survives, and therefore how much time planets have to form before the raw material is blown away. Smaller, dimmer stars blow away their disks more slowly, giving planets more time to grow. Larger, brighter stars clear their disks faster, potentially cutting short the planet formation process. All of these phenomena, from solar sails in Earth orbit to the explosion of massive stars, from optical tweezers trapping cells to the regulation of black hole feeding, are manifestations of the same physics. Photons carry momentum. When photons interact with matter, they transfer that momentum. Each individual transfer is tiny, but the universe produces photons in such staggering numbers that the collective effect is enormous. Let me bring this back to the core of our story, because sometimes when people hear about radiation pressure and solar sails, they think of it as something exotic or unusual, but it's not. It's happening everywhere, all the time, at every scale. Right now, at this very moment, sunlight is pushing on the Earth. The total radiation force from the sun on our planet is roughly 584 million newtons. That sounds like a lot, and it is a lot in absolute terms. But Earth is massive. Its gravitational attraction to the sun is about 3.54 times 10 to the 22 newtons. The radiation force is less than a billionth of the gravitational force. So Earth's orbit is barely affected, but it is affected. Radiation pressure contributes a tiny perturbation to Earth's orbit, one that astronomers can calculate and that must be accounted for in the most precise orbital models. Sunlight pushes on every satellite in orbit. For large, lightweight satellites with big solar panels, the radiation pressure can cause measurable orbital drift over time. Satellite operators have to account for this. It's a real engineering consideration, not a theoretical curiosity. Sunlight pushes on every grain of dust in the solar system. For very small dust particles, the ones just a few micrometers across, radiation pressure can actually exceed the sun's gravitational pull. These tiny grains get blown out of the solar system entirely, pushed into interstellar space by nothing but sunlight. This is why interplanetary space isn't choked with dust. Sunlight continuously sweeps the smallest particles away. Sunlight pushes on the tails of comets. When a comet approaches the sun, solar radiation vaporizes ices on its surface, releasing gas and dust. The dust particles get pushed away from the sun by radiation pressure, forming the dust tail that always points roughly away from the sun. The gas tail is pushed by the solar wind, which is a stream of charged particles, not photons. But the dust tail is shaped primarily by photon momentum. Every photograph you have ever seen of a comet with a graceful, curving tail is a photograph of photon momentum in action. What strikes me about all of this is the sheer range of scales over which photon momentum operates. The same physics that traps a single bacterium in the focus of a laser beam also shapes the tails of comets, drives the winds of massive stars, limits the maximum size of stars in the universe, regulates how fast black holes consume matter, and could one day propel humanity's spacecraft to other worlds. A single photon of visible light carries about 10 to the minus 27 kilogram meters per second of momentum. That's so small it borders on nothingness. And yet, collect enough of these nothings together, aim them in the same direction, let them accumulate over time, and they become a force that shapes the cosmos. This is the remarkable thing about photon momentum. It's not dramatic on the individual scale. A single photon doesn't slam into a surface with a satisfying impact. It arrives silently, invisibly, transferring a quantity of momentum so small that no human sense could ever detect it. But the universe deals in numbers so large that even the smallest individual contribution, multiplied by trillions upon trillions, becomes powerful. A gentle rain of photons, arriving ceaselessly, each one delivering its whisper of a push, adds up to a shout that can move spacecraft, trap cells, drive stellar winds, and sculpt nebulae. But we haven't yet seen the most direct, the most elegant proof that photons carry momentum. Everything I've described so far, solar sails, optical tweezers, radiation pressure on stars, these are all consequences of photon momentum. They demonstrate that the momentum is real by showing its effects. But there's one experiment that doesn't just show the effects, it shows the momentum transfer happening, photon by photon, directly, unmistakably, in a way that leaves no room for doubt. That experiment changed physics forever, and it's where we're going next. In 1923, an American physicist named Arthur Holly Compton performed an experiment that changed physics forever. It was elegant, decisive, and impossible to explain unless photons carry momentum. Before Compton's experiment, physicists had strong theoretical reasons to believe photons carry momentum. Einstein's relativity demanded it. Maxwell's electromagnetism predicted it. The mathematics was clear. But there is always a difference between mathematical prediction and direct experimental proof. Compton provided that proof. Here's what he did. He aimed a beam of X-ray photons at a block of graphite, which is a form of carbon. X-rays are photons, just like visible light, but with much shorter wavelengths and much higher energies. When the X-ray photons struck the graphite, most of them passed through or were absorbed, but some of them bounced off the electrons inside the carbon atoms. These scattered photons came out at various angles, and Compton carefully measured their wavelengths after scattering. What he found was remarkable. The scattered X-rays had longer wavelengths than the original beam, and the amount by which the wavelength increased depended on the angle at which the photon scattered. Photons that scattered straight backward, bouncing back the way they came, had the greatest increase in wavelength. Photons that scattered at shallow angles, barely deflecting from their original path, had very little change in wavelength. Photons that passed straight through without scattering had no change at all. This pattern was impossible to explain if light was a classical wave. Classical wave theory predicted that the scattered X-rays should have exactly the same wavelength as the incoming beam, regardless of the scattering angle. There was no mechanism in classical physics for a wave to change its wavelength, simply by bouncing off an electron. But the pattern was perfectly and precisely explained if you treated the X-ray beam not as a continuous wave, but as a stream of individual photons, each carrying a specific energy and a specific momentum. Compton analysed the scattering using the same physics you'd use to analyse a billiard ball collision. A photon comes in with known energy and known momentum. It strikes an electron. The photon bounces off in one direction. The electron recoils in another direction. Energy is conserved. Momentum is conserved. Both energy and momentum must balance perfectly before and after the collision, just like in any collision between two objects. When Compton worked out the math, treating the photon as a particle with momentum equal to its energy divided by the speed of light, he got a prediction for exactly how much the wavelength should change at each scattering angle. His prediction matched the experimental data perfectly, every single data point. The agreement was exact. Let me walk through what happens in a single Compton scattering event so you can see why it's so powerful as evidence. Before the collision, the X-ray photon is traveling in a specific direction with a specific energy and a specific momentum. The electron in the graphite is essentially at rest, sitting in the atom with negligible momentum compared to the incoming photon. After the collision, the photon has changed direction. It's now moving at some angle relative to its original path. And because it transferred some of its energy and momentum to the electron, the photon now has less energy than it started with. Less energy means lower frequency. Lower frequency means longer wavelength. The photon has been redshifted by the collision. Meanwhile, the electron has been knocked free from the atom and is now moving in some direction, carrying the energy and momentum it received from the photon. If you add up the energy of the scattered photon and the energy of the recoiling electron, you get exactly the energy of the original photon. If you add up the momentum vectors of the scattered photon and the recoiling electron, you get exactly the momentum of the original photon. The books balance perfectly. The amount of wavelength increase has a specific formula, now called the Compton scattering formula. It depends on only two things: the angle at which the photon scatters and a fundamental constant called the Compton wavelength of the electron. That constant is determined by the electron's mass and Planck's constant, nothing else. The formula has no adjustable parameters. You can't tweak it to fit the data. It either matches or it doesn't. And it matches, precisely. Across every angle, every energy, every material, the Compton formula works. This was the experiment that convinced the physics community once and for all that photons are real particles carrying real momentum. Before Compton, many physicists were willing to accept that light came in quanta, discrete packets of energy as Planck and Einstein had proposed, but some still resisted the idea that these quanta behaved like particles with definite momentum that could be exchanged in collisions. Compton's experiment ended that debate. You cannot explain the wavelength shift without giving the photon momentum. Classical waves don't behave this way. Only particles with energy and momentum colliding with other particles produce this pattern. Arthur Holly Compton received the Nobel Prize in Physics in 1927 for this discovery. Compton scattering is not just a historical curiosity. It happens constantly throughout the universe, every time a high-energy photon encounters a free electron, whether in a laboratory, inside a star, in the plasma surrounding a black hole, or in the thin gas between galaxies, Compton scattering can occur. The photon transfers some of its energy and momentum to the electron, changes direction, and continues with less energy and a longer wavelength. In some extreme environments, the reverse happens. High-energy electrons can transfer energy to low-energy photons, boosting them to higher energies and shorter wavelengths. This is called inverse Compton scattering, and it's an important process in astrophysics. It helps explain how certain sources in the universe produce extremely high-energy gamma rays. The cosmic microwave background, the ancient afterglow of the Big Bang that fills all of space, has been slightly modified by Compton scattering. As this ancient light passes through clusters of galaxies, it encounters hot electrons in the gas between galaxies. These electrons boost the energy of some of the photons through inverse Compton scattering, creating a measurable distortion in the background radiation. This effect, called the Sunyaev-Zeldovich effect, is used by astronomers to detect and study galaxy clusters. It's a direct, practical application of photon momentum exchange happening across billions of light years. Now let's talk about something that changes how we measure photon momentum without changing the photon's fundamental nature: redshift. When we observe light from distant objects in the universe, that light is often redshifted. Its wavelength has been stretched, shifted toward the red end of the spectrum. There are several causes of redshift, but the most important for cosmology is the expansion of space itself. As the universe expands, the space through which a photon travels stretches. The photon's wavelength stretches along with it. By the time the light from a distant galaxy reaches us, its wavelength might be several times longer than it was when it was emitted. A longer wavelength means lower frequency. Lower frequency means less energy because energy equals h times f, and less energy means less momentum because momentum equals energy divided by the speed of light. So a redshifted photon has less measured energy and less measured momentum than the same photon had when it was first emitted. But here's the crucial thing. The photon didn't slow down. In vacuum, the photon still travels at exactly the speed of light. It always has, and it always will. Its speed hasn't changed. What changed is its energy and momentum. And it's important to understand why this doesn't violate any conservation law. The photon's energy and momentum weren't lost. They weren't destroyed. They were transferred to the fabric of space itself, in a manner of speaking. The expansion of the universe is a property of space-time. As space expands, the energy of photons traveling through it decreases. This is a well-understood consequence of general relativity, Einstein's theory of gravity and curved spacetime. The energy doesn't vanish into nothing. It's accounted for in the dynamics of the expanding universe. The mathematics of general relativity handles this bookkeeping consistently, though it's more subtle than the straightforward conservation laws of Newtonian physics. The practical result is simple. When you observe a photon from a distant galaxy, the energy and momentum you measure depend on how much the universe has expanded since the photon was emitted. A photon from a galaxy 10 billion light years away has been traveling for 10 billion years. During that time, the universe has expanded significantly. The photon arrives with much less energy and much less momentum than it had when it was first created. But at every point along its journey, the photon was traveling at the speed of light. It was always a photon. It always had energy and momentum linked by the same relationship. The values just changed gradually as space stretched beneath it. This connects to a deeper point about photon momentum that's worth emphasizing. Photon energy and momentum are not absolute, fixed numbers that every observer agrees on. They depend on the relative motion between the photon source and the observer. This is true even without the expansion of the universe. It's a consequence of special relativity. Imagine a flashlight emitting green photons. If you're standing still relative to the flashlight, you measure the photons as green with a specific energy and a specific momentum. Now imagine you're moving toward the flashlight at high speed. The photons you receive are blue shifted. They have shorter wavelengths, higher frequencies, more energy, and more momentum than they would if you were standing still. Now imagine you're moving away from the flashlight at high speed. The photons you receive are red-shifted. Longer wavelengths, lower frequencies, less energy, less momentum. The photon itself hasn't changed. It was emitted with a specific energy in the frame of the flashlight, but your measurement of that energy and momentum depends on your motion relative to the source. Two observers moving at different velocities relative to the same light source will measure different energies and different momenta for the same photon. Both measurements are correct. Neither observer is wrong. Energy and momentum are relative quantities that depend on the observer's frame of reference. This is not a flaw or a complication. It's a feature of how the universe works. Einstein's relativity tells us that there is no single, absolute frame of reference from which to measure things. Different observers in different states of motion are equally valid, and they will measure different values for quantities like energy and momentum. What remains the same for all observers is the relationship between these quantities. The equation connecting energy, momentum, and rest mass holds in every frame. For a photon, the rest mass is always zero in every frame. The speed is always the speed of light in every frame. But the energy and momentum can differ, and that's perfectly consistent. This observer dependence has real physical consequences. In particle physics, whether a photon has enough energy to produce a particle-antiparticle pair depends on the frame of reference. In astrophysics, the energy of cosmic background photons as measured by a fast-moving particle can be much higher than the energy measured by a stationary observer. High-energy cosmic rays, protons moving at nearly the speed of light, see the cosmic microwave background photons as extremely energetic gamma rays in their own rest frame. This leads to interactions that would be impossible if both the proton and the photon were at rest. The momentum of a photon is real, but its measured value depends on who is doing the measuring and how they're moving. This observer dependence of photon momentum isn't just a theoretical curiosity. Physicists have turned it into one of the most remarkable tools in all of modern physics. A tool that uses photon momentum to do something that sounds impossible, to to make things colder. The technique is called laser cooling, and it exploits the fact that when an atom moves toward a photon source, the photon's frequency appears slightly higher from the atom's perspective, blue shifted by the Doppler effect. When the atom moves away from the source, the photon appears slightly lower in frequency, red shifted. Physicists realize that by tuning a laser to a frequency just slightly below the natural absorption frequency of an atom, they could create a situation where only atoms moving toward the laser would absorb the photons. An atom moving toward the laser sees the photons as blue shifted, nudged up to exactly the right frequency for absorption. The atom absorbs the photon and receives a momentum kick in the direction opposite to its motion. The kick slows it down. An atom moving away from the same laser sees the photons as red-shifted even further from the absorption frequency, and doesn't absorb them at all. It sails on unaffected. The result is a force that selectively slows atoms that are moving toward the laser while ignoring atoms moving away from it. Shine lasers from all 6 directions, left and right, up and down, front and back, and every atom in the sample, no matter which direction it's moving, encounters a laser beam pointing against its motion. It absorbs photons from that beam and gets slowed down. In every direction, atoms are being hit by photon momentum kicks that oppose their movement. What about the photons that get re-emitted after absorption? The atom doesn't keep the energy forever. It re-emits a photon as it drops back to its lower energy state. But the re-emitted photon goes in a random direction. Over many absorption and re-emission cycles, the momentum kicks from the re-emitted photons average out to 0, because they point equally in all directions. But the momentum kicks from the absorbed photons don't average out because those photons all come from the laser beams and always push against the atom's motion. The net effect is cooling. The atoms slow down. Their kinetic energy drops. They get colder. This technique can cool a cloud of atoms from room temperature, where atoms move at hundreds of meters per second, down to temperatures measured in millionths of a degree above absolute zero. At these temperatures, atoms move at speeds of only a few centimeters per second. They're nearly motionless, and they were slowed to a near standstill by nothing but photon momentum. Laser cooling earned the Nobel Prize in Physics in 1997 for 3 physicists: Stephen Chu, Claude Cohen-Tanuji, and William Phillips. Each had developed crucial techniques for trapping and cooling atoms with light. Their work opened the door to Bose-Einstein condensation, the creation of a new state of matter that only exists near absolute zero. It enabled atomic clocks of extraordinary precision, clocks that lose less than 1 second over billions of years. It led to breakthroughs in quantum computing and quantum simulation. All of this from photon momentum. Each time a laser photon hits an atom head-on and is absorbed, the atom slows down by a tiny amount, a few centimeters per second per photon absorbed. But repeat this process millions of times per second, and the atom is brought to a near standstill. Light, which normally warms things up, is being used to cool them down, not by removing energy through some refrigeration cycle, but by using the directed momentum of photons to oppose atomic motion and drain kinetic energy from the system one kick at a time. This is photon momentum at its most refined. Earlier tonight, we established that photons must carry momentum because of the relationship between energy and the speed of light. We saw that the emitting atom recoils when it creates a photon. We saw that absorbing atoms receive a momentum kick in the direction the photon was traveling. And now, In laser cooling, all of those principles combine with the observer dependence of photon frequency to create a tool so powerful that it can bring matter to the coldest temperatures ever achieved in the universe. Colder than anywhere in nature. Colder than the deepest void between galaxies. Colder than the cosmic microwave background itself. All accomplished by the momentum of massless particles of light. Now, I want to briefly address a topic that many people wonder about when they learn that photons carry momentum. What happens to photon momentum inside a material? Inside glass or water or a crystal? This turns out to be a surprisingly complicated question, one that physicists have debated for over a century. In vacuum, photon momentum is clean and unambiguous. Momentum equals energy divided by the speed of light. There's no material to interact with, no medium to complicate things. But when light enters a material like glass or water, it slows down. The speed of light in glass is about 2/3 the speed of light in vacuum. The speed of light in water is about 3/4 the speed of light in vacuum. The light is still electromagnetic radiation, still made of photons, but it's propagating through a medium where it constantly interacts with the atoms of the material. The question is, what is the momentum of a photon inside this material? Two different answers were proposed over a century ago, and both have some validity. In 1908, the German physicist Hermann Minkowski argued that the momentum of light in a medium should be higher than in vacuum, proportional to the refractive index of the material. In 1909, the German physicist Max Abraham argued the opposite, that the momentum should be lower, inversely proportional to the refractive index. Both predictions lead to different experimental consequences, and experiments over the decades have seemed to support both answers at different times, depending on the setup. This is known as the Abraham-Minkowski controversy, and it's one of the longest running debates in physics. The resolution, as best we understand it today, is that both answers are correct, but they're answering slightly different questions. When light enters a material, it doesn't travel as a bare photon. It forms a coupled system with the material. The light and the atoms of the medium interact continuously. The photon is absorbed and re-emitted, scattered and redirected countless times as it passes through. The total momentum of this coupled system, the light plus the material response it induces, is what's physically meaningful. And depending on whether you're asking about just the electromagnetic part of the momentum or the total momentum, including the material's response, you get different answers. Both the Abraham and the Minkowski momenta correspond to real, measurable physical quantities. They're just measuring different aspects of the same coupled system. For our story, the important point is this: the complications of momentum inside materials don't change anything about the fundamental physics. In vacuum, photon momentum is clean, exact, and unambiguous. Inside materials, things get more complicated because the light and the material form an intertwined system, but the core truth remains. Photons carry momentum. That momentum is real, and it is transferred to matter during absorption, reflection, and scattering, whether that matter is in vacuum or embedded in a medium. Now let's come back to where we started. Let's answer the question in the title directly and completely. Where does a photon get its momentum from? The answer is that a photon does not get its momentum from anywhere in the way you might expect. It doesn't collect momentum during a journey. It doesn't pull momentum from the vacuum. It doesn't carry hidden mass that secretly provides the momentum, and it definitely doesn't accelerate from rest. A photon's momentum is created in the same instant the photon itself is created. The two are inseparable. They are the same event. When a system undergoes an energy transition, whether it's an electron dropping to a lower energy level in an atom, a nucleus releasing a gamma ray, or a charged particle decelerating and radiating, the transition releases energy in the form of a photon. The photon is created moving at the speed of light, with a frequency determined by the energy of the transition. And because of the deep relationship between energy, momentum, and the speed of light encoded in Einstein's relativity, that energy automatically comes with momentum. You cannot have a photon with energy but no momentum. The two are locked together by the structure of space-time itself. The source of the photon supplies the energy, and the source recoils to conserve momentum. If an atom emits a photon to the right, the atom recoils to the left. The photon's rightward momentum and the atom's leftward momentum sum to whatever the total momentum was before the emission. Nothing is created from nothing. Nothing appears out of the void. The energy comes from the transition. The momentum comes from the energy. The recoil balances the books. The photon then carries that momentum through space, transported by the electromagnetic field, at the speed of light, unchanged and unchanging until it encounters matter. When it does, it transfers its momentum through absorption, reflection, or scattering. The receiving object recoils, momentum is conserved again. The chain is unbroken from creation to destruction. The everyday formula, momentum equals mass times velocity, is not wrong. It's incomplete. It's a special case that works for massive objects at ordinary speeds. The complete picture, given by Einstein's energy-momentum relation, shows that energy itself carries momentum when it moves through space. Mass is one form of energy, and so massive objects carry momentum through their mass and velocity, but energy can exist without rest mass. A photon's energy is pure electromagnetic oscillation, a vibration of the field at a specific frequency. That oscillation, moving through space at the speed of light, carries momentum in exact proportion to its energy. No mass required. This is not a loophole or a special exception. It's the natural, beautiful, inevitable consequence of how energy, space, time, and momentum relate to each other in our universe. Einstein didn't add photon momentum as an afterthought. It fell out of the equations on its own, as naturally as water flows downhill. Set the rest mass to zero in the energy-momentum relation, and you get momentum equals energy divided by the speed of light. The photon was always there in the mathematics, waiting to be understood, and the evidence is overwhelming. Compton scattering proved that photons exchange momentum with electrons in exactly the way particle physics predicts. Solar sails accelerate in space, pushed by nothing but reflected sunlight. Optical tweezers trap living cells using the momentum of focused laser light. Laser cooling brings atoms to near absolute zero using nothing but directed photon kicks. Radiation pressure supports stars against gravitational collapse, limits the maximum mass a star can achieve, drives stellar winds that shape nebulae, and regulates how fast black holes consume matter. Comet tails stream away from the sun, sculpted by photon momentum. Satellites drift in orbit because sunlight pushes on their solar panels. Tiny dust grains are blown out of the solar system entirely by the pressure of starlight. All of this, every single one of these phenomena, traces back to one simple truth. A photon carries momentum equal to its energy divided by the speed of light. That momentum is real. It pushes real things. and it originates in the same emission process that creates the photon itself. There is something deeply satisfying about this answer. The universe doesn't cheat. It doesn't create momentum from nothing. It doesn't hide mass inside massless particles. It doesn't bend its own rules. What it does is far more elegant. It reveals that our intuitive understanding of momentum, the understanding based on throwing balls and pushing carts, was too narrow. Momentum isn't about mass. Momentum is about energy moving through space. Mass happens to be one very common form of energy. So most of the momentum we encounter in daily life involves massive objects. But the deeper truth is that any energy traveling in a direction carries momentum. Light is energy traveling in a direction. Therefore, light carries momentum. We began tonight with a paradox. Something with no mass pushes real objects. We trace the answer through 4 connected revelations. First, that Newton's formula is a special case, and that Einstein's deeper relationship links energy to momentum even when rest mass is 0. Second, that the photon is born with its momentum fully formed in a single instant, paid for by the recoil of the source, so that no momentum appears from nowhere. Third, that when photons meet matter through absorption, reflection, or scattering, they deliver that momentum as a physical force, a force that traps cells, propels sails, shapes stars, and sets the upper limit on how massive a star can be. And fourth, that direct experiments, from Compton's X-ray collisions to modern laser cooling, confirm photon momentum with a precision that leaves no room for doubt. These are not 4 separate stories. They are one unbroken chain. A source undergoes an energy transition. A photon is created, already at full speed, carrying energy and momentum linked by relativity. The source recoils. The photon travels through the electromagnetic field. It meets matter. It delivers its momentum. The matter recoils. At every link in this chain, the universe's books are perfectly balanced. No momentum is created. No momentum is lost. It is simply passed from source to photon to matter, conserved at every step, from creation to absorption. And so, the next time you stand in sunlight and feel its warmth on your skin, remember this. That warmth is energy being absorbed, but alongside that energy, there is momentum. Each photon that lands on your skin carries a tiny, imperceptible push. Trillions of photons per second, each one delivering its whisper of momentum, each one pushing you with a force too small to feel but too real to deny. You are being pushed by light right now, gently, constantly, invisibly, pushed by something with no mass at all. The photon does not need mass to push you. It needs only energy and direction, and those it has carried since the instant it was born.